Welcome everyone to the final problem of the chaotic review. This is problem number 12. In this problem we're trying to sketch the graph of capital F of x, which is the antiderivative, right, or the indefinite integral of little f of x, given that f of 0 is equal to 1. Okay, so let me first of all say that this question right here, this problem would not make a great exam question because it doesn't go into enough detail, right? It doesn't specify how detailed of a sketch do we actually want, right? Because curve sketching, right, or sketching a graph of a function, right, this was in 3.5 and this was quite detailed, right? All of the techniques that we needed to do in order to sketch a graph. Remember, we had asymptotes, we had even and odd, and we had increasing, decreasing, concave up, concave down, all that sort of stuff. Right, and so in this case, right, it's not very specific. So I'm going to go over what I think would be a good enough solution in this case. But again, kind of in an exam question, they would have to specify what exactly do they want you to do. Kind of similar to some of the previous, exam 2s and stuff like this, where we had curve sketching as part of the questions, right? It actually told you exactly, find the intervals in which it's concave up, find the intervals in which it's increasing, all that sort of stuff. But in this case, right, this is a fine review question because it gets us thinking about it. Okay, so let's go ahead and try to identify maybe some of the increasing, decreasing, concave up, concave down stuff, all that good stuff. So I'm going to go ahead and calculate out the derivative of capital F. So as I was to calculate out the derivative of capital F, well, remember this is an antiderivative. So if you want to calculate out the derivative, well, you would take the derivative of the antiderivative and you should get back to where you started, right? This is really the first fundamental theorem of calculus. Or even really before that, just in the definition of the antiderivative more than anything. So if I take the derivative here, I should get back to x squared plus 2x minus 3, because again, this is notation that means the antiderivative. All right, so there is my derivative. So let's try to figure out where this function is increasing and decreasing. So that's maybe my first bit. I'm going to figure out where it's increasing or where is it decreasing. That's where the derivative is positive versus when is it negative. And so the technique here, right, is we try to figure out when it's equal to 0. This helps us split up the number line. So let's see, x squared plus 2x minus 3. I can go ahead and factor that. I feel like I've done it several times now throughout these videos. So I get x plus 3 and x minus 1. That's where it's equal to 0. So this is going to say at x equals negative 3 and at x equals 1, we have the derivative is equal to 0. The derivative of capital F is equal to 0. So let's go ahead and break up our number line here at negative 3 and at 1. Now we choose test points. So for instance, negative 4 or maybe 0 or 2, things like this. When we plug them into our derivative, right, our f prime, and we try to figure out is that derivative positive or negative, because that's going to tell us something about increasing or decreasing. So for instance, if I plug in negative 4 into my derivative here, let's see, I'm going to have 16 plus negative 4 times 2, that's actually going to be negative 8 minus 3, so that's going to be 5. And the big thing here is that it's greater than 0, so on this interval, it's positive. If I was to plug in 0, I'd have 0 plus 0 minus 3, so that's going to be equal to negative 3, and that's certainly negative. And if you were to plug in 2, I would get 4 plus 4 minus 3, so that's going to be 8 minus 3, that's 5, and that's certainly greater than 0. So I have positive, negative, positive. So remember, a positive derivative means it's increasing, a negative derivative means it's decreasing, and a positive derivative means it's increasing. So we can say that f, capital F here, is increasing on, let's see, negative infinity until negative 3, and then again from 1 to infinity. Likewise, f is decreasing on the interval from negative 3 to 1. That's a horrible one. There we go. So that's stuff about increasing and decreasing. Now let's talk about concavity. So let's do concave up versus concave down. So concavity has to do with the second derivative. So if I was to take the derivative of the derivative, I would get the second derivative, and that's going to be 2x plus 2. Same sort of deal here, same steps, right? I want to figure out when is this equal to 0, because that's going to help me break up my number line. So if I draw a number line down here, so let's figure out when this is equal to 0. So I subtract away 2, I'm going to get negative 2 is equal to 2x, and that gives me a x is equal to negative 1. So at negative 1, I break up my number line. Now I choose test points. So maybe something like -2 and something like 0, something in each one of these subintervals. And if I plug in -2 into my second derivative, I'm going to get 2 times -2 plus 2. So it's going to be -4 plus 2, so that's going to be equal to -2. That's certainly less than 0. And if I plugged in something like 0, I would have 0 plus 2, that's equal to 2, which is certainly greater than 0. So this is indicating, right, f is concave up on the interval from -1 to infinity, and f is concave down on the interval from -infinity to -1. Right, so that's how I read my graph here. Remember, this is about the second derivative. So maybe I'll include the f double prime over here. Okay. So I'm going to use this information along with the fact that if I plug in 0, I get out 1 in order to do a sketch of the graph. So let's go ahead here. I'm going to make out my graph. I know at f of 0 I get 1. So f of 0 I get 1. So I'm going to go ahead and maybe place a dot. I'm going to use purple, I suppose. So purple right here. So at f of 0 I get 1. And then I have some key points, right? So I have at -3, that's somehow key. 1, 2, 3. So that's -3. So something's changing at -3. I'm going to just do a dashed line here. And then let's see, at -1, something's changing. So at -1, let me go ahead and do a dashed line here. And then also at 1, something's changing. So at 1, something's changing. So let me go ahead and break it down like this. All right, so let's see, when I'm less than 3, I have a positive derivative. That means I'm increasing. So I'm going to go ahead and write increasing here. And then let's see, between -3 and 1, I'm decreasing. So here I have decreasing, and here I have decreasing, all the way up to 1. And then after 1, I'm increasing again. Okay, how about stuff with the concavity, right? Below -1, I'm concave down, right? So I'm going to do concave down, concave down. But then after -1, I'm concave up. So I'm going to do concave up, concave up. So I'm just going to do the C's with the little arrows here to stand for concavity. Okay, and now I've kind of embedded all of the information about increasing and decreasing, concave up, concave down, and of course I have this f of 0 equals 1 into my graph. The last thing to do is actually sketch a picture. So, okay, let's start in this interval here. I'm decreasing and yet concave up. So decreasing and yet concave up. So I should look something like this. So decreasing and concave up. After that, I'm increasing and concave up. So something like this maybe, increasing and concave up. Okay, on this interval here, I'm decreasing and concave down. So maybe I need to start up higher here, decreasing and concave down. So, okay. And then finally, before -3, I'm increasing and concave down. So I'm increasing, but I'm doing it slower and slower, right? I'm increasing and concave down. So something like this. So this is a rough sketch, and in fact from this rough sketch, although it didn't specify really at all, but we could also identify some specialty points, right? So for instance, at -3, we have this is a local max. Likewise, at -1, right, we actually switch concavity. It was concave down and now it's concave up. This is going to be an inflection point. And then finally, maybe at 1 here, this is a local min, because it switches from decreasing to increasing. So we can even identify some of those specialty points. But this is now a rough sketch of capital F, or the antiderivative of our function x squared plus 2x minus 3. All right, that's it for this video, and that's it for the chaotic review. Thanks for watching, guys. I'll see you next time.